Hi, hello everyone. Welcome to my presentation. So today I will show you how we can mitigate ROM in a scalable way with a full in DRAM mitigation. I'm Michele Marazzi from ETH Zurich, and this was done in collaboration with Zentel Japan, which is a DRAM vendor. So all of these devices have in common that they rely on DRAM memory. Unfortunately, in 2014, it has been shown to be vulnerable to ROM. Now, since then, we have seen that the vulnerability got much worse, but the mitigations are not scaling with the trend. So in this presentation, I will show you how we can actually achieve protection for many years to come. So before getting to Rega, we need to introduce some DRAM basics. So the memory inside the DRAM chip is organized in many rows and many columns. And when the memory controller wants to use some memory, it needs to first activate the corresponding row by issuing an activation. And then it can, for example, issue a read or a write by specifying a column. When it's over, it can issue a precharge, which will deactivate the row. So if we imagine to zoom in on rows in a DRAM chip, we will see that they're actually made of capacitors. Unfortunately, capacitors leak charge. For this reason, the DDR standard requires the memory controller to periodically issue refresh. And this refresh ensure that every row will be refreshed at least once in 32 milliseconds, for example, for DDR5. Unfortunately, ROM accelerates this leakage, and this acceleration is given by the activation of nearby rows. So, for example, if a cell is having a high-value charge, that might represent a logic 1, and enough activations are issued to its nearby row, then it will have leaked enough charge so that its value will be interpreted as a 0 and not as a 1 anymore. And we call this bit flip. So you might ask, okay, how many activations are we actually talking about? Well, in 2020, it has been shown that as little as 10,000 activations are necessary to induce a bit flip, which takes less than 1 millisecond. So you can see why the refresh alone cannot really compensate for this problem. Of course, there are deployed mitigations inside the DRAM chip to try to protect from the hammer, and these are known as TRR, or target row refresh. And they work as follows. Basically, the DRAM chip receives a series of activations that may be from an attack or maybe from a normal load, and then eventually they receive this refresh. Now, from time to time, instead of doing its normal job, the time of this refresh is hijacked into selecting a row or multiple rows that are considered to be a victim, and then refreshing them. So why is this not working? Well, we need to look at two factors that represents the row hammer trend. So on one side, there is the fact that the threshold is severely dropping. Please note that this is a logarithmic scale. And already for the current years and the current threshold, my colleague Patrick has shown last year here at SMP that he could actually get bit flips on every single DDR4 device tested. So it's easy to assume that the future will be very challenging. And on the other side, the blast diameter is increasing. Now, the blast diameter is how many rows are affected by a single activation, basically how many victims are generated by one aggressor. And originally, it was considered to be only the direct adjacent ones. Then last year, with half double, we have seen that it might actually be up to 4. But the JEDEC standard is already talking about 6 rows. So why are these two factors problems for mitigations? Well, because the refresh is periodic, and this means that the device has a limited refresh capability. So whenever there is a refresh, it needs to make wise decisions. It needs to understand and select the corresponding real victim row. And this translates to have states and memory. And this memory increases and increases as the threshold drops. And we have shown this last year with ProTRR, which is an in-DRAM hammer mitigation, that as the threshold gets lower and lower, it becomes unpractical to be deployed. And this gets worse if higher blast diameter are considered. So on one side, you could achieve a secure TRR implementation, but it becomes unpractical for lower thresholds. So can we avoid at all the need to track rows? Or in other words, can we increase the refresh capability? And the answer is yes. This is exactly what Rega does. Rega takes one activation, and it transforms to a potential refresh. So what we want is a blast diameter independent hammer mitigation that scales to low thresholds and that is fully in DRAM. And what we want to do is that whenever we receive an activation, we want to perform two parallel things at the same time. On one hand, we want to handle the requested row as the device would normally do. On the other hand, we want to perform an extra row refresh, which we call shadow row refresh. And how do we pick this shadow row? Well, we perform round robin across all the rows in a subarray. So after enough activations are received, all the rows will be refreshed. So remember, the activation I showed you at the beginning is actually more complex, and internally is made by other steps. In particular, we have the charge sharing operation and the latching operation. And then remember, there is the read and write. Well, all of these depend on the sense amplifier, which is a component inside the DRAM chip, which in simple terms is connected to a row via column or bit lines. Now, the real world is more complex, and we should be talking about many capacitors in parallel, many sense amplifiers in parallel. But for simplicity of this presentation, let's keep row and sense amplifier. So the first step is the charge sharing operation. In this operation, in this step, the cell shares its charge to the sense amplifier. And please keep in mind that this is a destructive operation. Then the sense amplifier can start reading or amplifying the value up to reaching a logical value. As it does so, it's also refreshing the row. When it's over, it has latched the value. It allows for read and writes, with the particularity that the write will be an instant write back. So why can't we already refresh the extra row? Well, if we look at the sense amplifier, it has two different tasks. On one hand, it needs to recharge the cell. On the other hand, it needs to handle read and writes. And handling read and writes keeps the sense amplifier busy, because this could happen at any point in time. And the DRAM device is a synchronous device, so it needs to respect the memory controller request. It cannot stall, it cannot do other things. However, we can decouple and parallelize these two operations simply by adding a new sense amplifier, which we call Rega sense amplifier, which will handle read and writes, acting in practice as a buffer. And for this reason, it can be smaller, while the original sense amplifier will do the heavy work of refreshing the row, and for this reason, will have its original size. So it works as follows. We receive an activation. We start the charge sharing and latching operation with the Rega sense amplifier, but then we switch to a different shadow row, and we start performing a parallel refresh. And this might take some time, and we might receive read or writes, but these are handled by the Rega sense amplifier. When the refresh is over, we perform a write back operation that both updates the value and also refresh the original requested row. So timing are important. Whenever we receive an activation, we lose control over these bit lines or over these columns when we receive a pre-charge. And this is defined by the standard to be at minimum TRAS. And we demonstrated that TRAS is enough to perform one shadow row refresh and the write back. And if we implement Rega this way as a mitigation, we can already protect devices with threshold as low as 1K with high blast diameter, for example, 8, with 0% performance overhead. However, the threshold is dropping. So we ask, can we actually do more? And the answer is yes. We can perform multiple shadow row refreshes and then eventually the write back by extending this TRAS value. And we defined in the paper Regem 1 for 1 extra row refresh up to Regem 8 for 8 extra row refreshes. So the paper had many challenges. I invite you to read it if you're interested in it. In particular, because we are changing the internal DRAM architecture, we need to be sure that the circuit keeps its reliability. Unfortunately, before making Rega public, there was no publicly available reliable DRAM model that would represent commodity and up-to-date chips. So to overcome this problem, we collaborated with Zentel Japan and we built RAM, which we also open sourced. And you can find the link to our GitHub on the paper or on our website. So what are we going to evaluate? We're going to evaluate the circuit reliability. We're going to evaluate the performance overhead due to the extension of TRAS. We're going to evaluate the power overhead due to the extra row refreshes and the area overhead due to the extra circuitry. And to do so, we used many different approaches. We used LTSpice for the analog simulation. We used Gen5 and DRAM Sim 3 to perform full system cycle-accurate simulation and benchmark SPEC 2017. And lastly, we also have an ASIC design in 12 nanometer to better understand area and static power overhead. So for one extra row refresh, you can see that Rega looks like it's very close to ProTRR. Unfortunately, it's true that ProTRR would allow, in theory, secure protection for such a threshold. However, it's unpractical to be deployed at this level. And as we increase the extra row refreshes, we get coverage among many years with performance overhead that passes from 0%, 0 point, up to the worst case of 8% for threshold as low as 128 and blast diameter as high as 8, but theoretically even more. And please note that threshold of 128 is extremely lower compared to previous work. We have a constant area overhead of around 2% independently from the Rohammer threshold or the blast diameter. And of course, the power overhead increases with the amount of extra row refreshes that we are performing. So to conclude, we develop Rega as an independent Rohammer mitigation from the blast diameter. It's compatible to the DDR standard, it scales to low threshold, and it's fully in DRAM. We also open source RAM, allowing for the first time researcher to actually have a reliable DRAM model. So thank you very much. I'm happy to take any questions.
Oh, thank you. If you have any questions, please come to the microphone in the middle.
It is great work, thank you. I'm really worried about that 26% power overhead, right? Dissipation is certainly a really big issue on high-speed DRAM today. Can you talk about like what the trade-off is there? Like what's the limit, right? Would you expect with sort of current designs, could we get 40% or is 15% sort of what's feasible without having to re-architect the power plane?
Yes, thank you for your question. Well, first, this is not a static power overhead, right? And it's obtained while we were benchmarking Spec 2017, which is a very, very heavy load. However, it's true, around 26 or 27 would be a really high power overhead. However, the condition of a threshold of 128 and blast diameter of 8 is so far from anything that previous work has considered that I believe the price, if we reach that threshold, would be justified. Thank you.
All right, so I have a question. You talk about the open source DRAM model.
Yeah.
Can you elaborate on what's it, how can it be used by other people?
Yeah, sure. So in this model, we describe the layout. Okay, now I may get a bit technical on the DRAM side, but we describe the layout of a mat, which describes exactly the sizes, the length, and the layout of the sense amplifier and the word line drivers. This for the first time. On top of this, we also add the line parasitics, such as resistive parasitics and capacitance parasitics, and we also add transistor sizes. Now, all of this information were previously unavailable, and the commonly used DRAM model was, as the author stated, a best guess. Now, why this is not optimal is because if you want to change the internal operation of, for example, the sense amplifier, you need to be sure that the timing of DRAM are respected. Now, if your parasitic capacitance is 10 times lower than it's actually in reality, then you're going to make your life very, very easy. And of course, the opposite would be true if you're considering a case that is extremely unrealistic. So in particular, how this would help future work is, for example, for Rohammer mitigation, if they want to add new precharge circuit, new sense amplifier circuit, different column accesses, and also in the direction of processing memory. So for example, there are many publications of Micro that propose processing memory applied on DRAM technology, and they are based on outdated DRAM model. So it's a bit uncertain to understand if once deployed, they would actually work. Thank you.
Thank you. Any more questions? Okay, so let's thank the speaker again.